Okay, so today we we're just going to keep trudging along on HVAC. So the load, we've talked about the load before. So recall that the load in a space in HVAC terms, that's the heat gained or the heat lost in a space or a building. Could also be described as what does a space need, either heating or cooling, to keep it comfortable? Because that has to be in balance. If a space is losing 100,000 BTUs per hour of heat, the heating system has to put back in the same amount. The load doesn't care what systems are serving it. So again, this kind of abstract quote, the load is the load. It doesn't care. But the energy to serve that load can vary significantly. So depending on the system type you have or the fuels you're using to get the same output could result in very different inputs depending on what kind of system you have. And recall the fundamentals that we talked about last time. Is my space hot? We're going to blow in cold air. If my space is cold, we're going to blow in hot air. So here is a schematic that I think probably looks a little better than the schematic I put together last time. But this shows some of the major components of an air handling unit. So you have your outdoor air in, your return air coming back from the space, a filter, which I don't think we really talked about a filter, but it's important to filter your air and get all the dirt out before it hits these coils because they will get very dirty very fast. You have your cooling coil, which has to have this drain pan to collect the condensate that will sweat out of the air, and a drain pipe that has to go to a floor drain somewhere. Heating coil and a fan, and then ultimately your supply air. An air handler in the real world would look something like this. And this would be a big air handler. Most of the air handlers I see are shorter than I am. Whereas this is a very large one that you can actually physically walk into all of these different components through these doors. And so we have our return air coming in the back. You can see this flexible connection on the duct. That's where our return air is coming in. Our outside air is coming in through the top. And then that air is mixing together somewhere in here. We have our filters and our coils buried somewhere in here. Our fan is probably the last thing in the line. And then we have our supply air leaving the unit out the top. So all those components are going to be in there. And in this particular case, they installed these doors so that you can physically walk into this thing and service those components. But like I said, this is a big unit. One thing that's not shown in either of these diagrams that just came to mind is they're not showing the relief. So recall, if we're bringing in outside air, we have to relieve the stale air in equal amounts, or else the building becomes pressurized. Sometimes that's built into the unit, but sometimes that relief happens somewhere else in the building. And that's probably what's happening in this case. I don't know if you've heard of the YouTube channel, The Engineering Mindset, but this guy can illustrate a lot of these concepts much better than I can because he is using actual animations. It's a very visual channel that shows how all this stuff comes together. So I highly recommend you take a peek at this video. I think it's about 13 minutes, but very useful information in there, and it shows things much clearer than I am. So the first system we're going to talk about, I'm going to try something here. We'll see how it works. Normally I have a whiteboard to have one thing up while I'm running through the slide. So this is to try to emulate that. So hopefully this is coming through okay. But the first and most basic system type is a single zone system. So a single zone system is the simplest type of system you can have, but is actually pretty decently efficient as far as HVAC goes. The reason being, it's only going to provide what's needed for each zone. And that's a big part of efficiency, is only providing what's needed and nothing more. And single zone systems do a pretty good job of that. You typically are going to have one room. I'm looking at the wrong system here. There we go. So you typically have one room with one thermostat and one dedicated HVAC unit to serve that one room or zone, which is why this is called a single zone system. This does require, though, numerous HVAC units throughout your entire building, because almost every room would require its own dedicated unit. If they're smaller rooms, you can get away with having one unit serve multiple rooms. But generally, you still need a lot of units to have single zone systems. And that's the biggest drawback. If you have a bunch of these units, there's lots of maintenance, because every single one of those has filters, it has a fan, it could have other components that need maintenance, and it takes up a lot of space to have a dedicated unit for every single zone. Pretty simple system. Is your room hot? You're going to turn on your cooling coil and provide 50 to 60 degree air out into the room, where it gets sucked back in, and then you just have this cycle that we talked about last time. Is your room cold? You turn on the heating coil and blow 85 to 100 degree air into the room until the thermostat says we're happy, we're comfortable. And then once you're comfortable, you're going to turn off the heating and the cooling at the air handling unit, but you still need to run the fans for ventilation. So that supply fan still needs to run all the time. When you're in that fan only mode, it's more moderate temperature air, somewhere in that 60 to 80 degree Fahrenheit range, depending on what the mixed air temperature would be between your outside air and your return air, because your heating and your cooling is off. But your heating and your cooling, it's only getting turned on as needed, depending on what that thermostat is calling for. So the heating and the cooling is cycled on and off, but the fan has to keep running all the time. I like to try to show this as what I call a system diagram. So what's going on in this unit as that thermostat is calling for heating or cooling? So this, I guess the x-axis down here, the heating demand between a full 100% heating demand and a 0% heating demand, and conversely a 0% cooling demand and a 100% cooling demand. That is all based on what this thermostat is asking for. The airflow is going to be constant because that fan is running all the time. So regardless of if I'm calling for heat or calling for cooling, my fan is just running all the time. But then on the heating side, well, if I have a 0% heating demand, my thermostat says I'm perfectly content, my heating's off. But as my heating demand increases, my heating output also has to increase until it's maxed out on a full heating demand call. And then on the other side, you have your cooling output, which is doing the same thing except on the cooling demand. So nice and low when there's no call, but it has to put out a lot of cooling energy when there's a large call for cooling. And so you just Notice the cooling output has to increase as the cooling demand increases, and same thing on the heating side. That's really all there is to a single zone system. Pretty simple and straightforward. The next system is a little more complicated. This is called a constant volume reheat system. One big difference here is this is one central air handling unit that serves multiple zones, and every one of those zones has its own thermostat. So that's a fundamental difference between this and a single zone unit, which is more on a one-to-one basis. We're still having a constant supply CFM of cool air. Well, I guess that's another thing that's different. I'll explain why that is in a second. But so this unit is still providing constant CFM, which is right in the name, constant volume. But it's always providing cold air. So coming out of this fan, this thing is always putting out somewhere in the 55 to 65. I see I listed a different temperature range here, but in any case, it's always cold, no matter what. And since that airflow is not changing, so each one of these zones that has their own thermostat, they are getting the same amount of CFM of cool air all the time. And the danger is that that means that these zones can start to subcool and get too cold because there's no way to control the cooling that they're getting. So the unit is basically, it's just full all out cooling output all the time. And then to prevent that subcooling from happening, every single zone has this reheat coil to heat up the air before it gets to the zone. So they're all getting cold air, and then this thermostat is telling this coil to heat up as needed to keep that thermostat happy. So it may be coming out at 55 degrees, and then it hits that coil, and maybe that coil heats it up to 70, and then it goes to the zone. Or maybe it heats it up to 90 degrees because the thermostat says, I need heating. I'm getting cold, so give me some hot air. The analogy here, imagine you're going to drive your car, keeping your foot fully on the gas, and then you're going to hit the brakes to control the speed, but your foot is on that gas all the time. That is what this system is like, because it's in full cooling mode all the time, and then you are counteracting that with these reheat coils downstream. So you can probably guess this is a pretty inefficient system. So if our room is hot, if our thermostat says, hey, we're getting warm in here, it will turn the reheat off and just allow that cold air to come through and be delivered into the room. But if the room is cold, then the thermostat will tell the reheat coil to turn down or turn off, or excuse me, backwards. The thermostat will tell the reheat coil to turn on and heat the air up before it gets delivered. So yeah, this is terrible efficiency. This is the worst possible system you can install in terms of efficiency, because you are essentially heating and cooling that air before it gets delivered to the space. You're cooling it at the unit and then heating it at these coils, and that takes a lot of energy. Current energy codes, they say no way. This is not going to fly. You cannot install this kind of system in today's industry, except in extremely rare exceptions. But one fundamental way to decrease the energy use of a system, an HVAC system, is to reduce that amount of simultaneous heating and cooling. This isn't the only system that has simultaneous heating and cooling. This is just the first example of it. Anything you can do to reduce that is going to save a lot of energy. And a quick definition on what I mean by that term, simultaneous heating and cooling. That means we are heating and cooling the air before it's delivered to the space, but that doesn't necessarily mean it's happening at the exact same time. But this is bad. This is a really bad thing in terms of energy use. Another system diagram. So same idea, the heating and the cooling demand as seen at the thermostat. So each one of these three zones would have its own independent diagram of what's going on. Our airflow, again, is still constant. We have no way to change how much air is going to each zone. Our cooling output is also constant because we're sending that 55-degree air all the time, regardless of what the thermostats are calling for. So we are pedal to the metal, foot on the gas all the time. And then our heating output looks a little strange. So when we are at a max cooling demand, so our thermostats are saying, hey, we are really warm in here, our heating output is essentially off, and our cooling output is just providing as much cooling as it can. But as that space starts to become satisfied, now we need to start turning on the heat. So if we're somewhere in here and the thermostat says, well, I need a little bit of cooling, you're still providing full cooling, and now you're turning on your heater, say 40%. And by the time you get to this full heating demand, now you are essentially entirely canceling out your cooling output and then some with your heat. So your cooling is peaked out, your heating is peaked out. So the most efficient point for this system is at this 100% cooling demand condition, because your heater's not running and you don't have that simultaneous heating and cooling, or at least in some of these zones, you don't have it. Maybe some of them have it a little bit. But then once you get into the winter months, now your heating and cooling systems are effectively fighting against each other. When all your thermostats are calling for heat, all those heaters are cranking along. That is your most inefficient point. So notice there's still heating output, even in that cooling demand, potentially still quite a lot. Cooling output 100% of the time. Yeah, I already talked about all this. All right. So next up, we have what's called a constant volume dual duct system. So similar to that constant volume reheat system, this is again one air handling unit that serves multiple zones. Each zone has its own thermostat. Again, we have a constant supply of airflow, so a constant CFM, and again, that is in the name, constant volume. That tells you that we're moving the same amount of air all the time. A big difference with a dual duct system is this is providing both hot air and cold air. So if you look at this diagram, you can see this is configured differently than everything we've looked at before, where our heating and our cooling coils are now in parallel rather than in series. And our cold and our hot air gets mixed before we finally deliver it to the space. So if we follow these lines, on the heating side, this unit is outputting hot air, and that's going out to all of our zones. It's putting out cold air, which is also going out to all of our zones. Then it gets mixed in this dual duct mixing box. And I'll show what this looks like a little more in depth here in a moment. In this mixing box, it mixes some of this cold air with some of this hot air to deliver some temperature of air in between those two incoming air streams. based on what that thermostat is calling for. The reason they call this a dual duct is throughout your building, you have two sets of ducts. You have your hot duct going everywhere and your cold duct. Every single room or zone, in this case, I'm showing 3 zones. Each room is always going to get the same total amount of airflow, but the mix of how much of that total is hot air versus cold air, that's what's going to vary. And that's what's going to influence your final temperature. Quick side note on terminology. When you're talking about a dual duct system, they use these terms called cold deck and hot deck, which you can probably guess. The cold air supply, that's your cold deck, and your hot air supply is your hot deck. And that is referring to the components at the air handling unit. That's not referring to anything downstream. So if our room is hot, so if this thermostat right here starts to say, hey, we're getting pretty warm in here, we're going to blend more cold air. So we'll allow more cold air on this side to come in, and we'll cut back on this hot air. And conversely, if we're cold, we want more of that hot air and less of that cold air. So it will act in a reverse response. This type of system, it's a little bit better than a constant volume reheat, but it's still really bad. The reason being, let's say this thermostat says, I'm perfectly happy where I'm at. I don't want heating. I don't want cooling. What that means is now we will split the difference to get about 50% hot air, 50% cold air to get us neutral air. Well, to get that neutral air, we still had to heat and cool air. So that would be the worst possible operating point for this system, is when the thermostat is perfectly happy. Because bottom line, if I want neutral air, that should not take a lot of energy to do that, but it does in this system. The dual duct boxes. So this is kind of a exploded view of what that looks like. So we have our hot deck air coming in, our cold deck air coming in. On each of these air streams, we have a damper that can open and close. And these two dampers are connected by a common motor, which is called an actuator. That thermostat feeds directly into that actuator and tells it what to do. So if we want more hot air, this actuator turns a certain direction, which opens the hot side and at the same time closes the cold side, and vice versa. Another YouTube video, which again, this can help illustrate more visually what's going on in these systems, talking about constant air volume systems, single zone, constant volume reheat, and constant volume dual duct. The next system type is what's called a multi-zone. This is a similar configuration to a dual duct system, very similar, in fact. In a dual duct system, we are ducting our hot air and our cold air throughout the entire building, and then we are mixing that air right before it's delivered to that space. So these boxes, these dual duct mixing boxes, these exist right before those ducts hit the room. So these dual duct boxes will be all over your building. A multi-zone, though, we are essentially doing the same thing, except we're mixing those air streams at the air handling unit instead. And then we're ducting it out to the spaces. These two system types, functionally identical From an energy use perspective, there's really nothing different about a dual duct versus a multi-zone. The only difference is in a multi-zone, you can see the mixing point is at the air handler itself, and then it gets ducted out all the way to your zones. So functionally, it's doing the exact same thing. We're just relocating where the mixing actually happens. We don't see a whole lot of dual duct and multi-zones today. They were extremely prevalent in the 1980s. This is more of a design consideration, but dual duct and multi-zones, even though they are terribly inefficient, they do provide really good comfort to the occupants in the space. In the 1980s, energy was dirt cheap, and they just didn't care. They knew these systems could deliver a high level of comfort, and that was all they really cared about. A lot of them now have been taken out. Like I said, today you can't really install these based on modern codes. So they're not common to see anymore, but when I see one, it's still not that surprising. So here's what a multi-zone unit would look like in real life. So we have our hot deck dampers. So behind all of these dampers would exist some sort of heating coil on the top half of this unit. Then we have our cold deck dampers on the bottom half. So our cooling coil would sit down here somewhere. And then we have all of our actuators up here on top. And those actuators control both halves of the damper in inverse proportion. And you can see based on the actuators where the zones are and how many zones they have. And you can see some zones have bigger dampers than others, which means that those zones are designed to be provided more airflow. This middle zone here requires significantly more airflow than this tiny one on the end. And so these yellow boxes, this would be where the duct connection point would be. So you'd duct around this entire connection right here and then send that out to that zone. And then the thermostat would control all of these actuators to change how the air is blending at the unit. Another more of a design consideration, but a lot of these multi-zone units were not really designed to be taken apart, which means these dampers, this whole bank of dampers, is often very difficult to get to and maintain. And sometimes it's just cheaper to replace the entire unit rather than trying to fix a bunch of broken dampers. Quick side digression. We've talked about constant volume, dual duct, and constant volume multi-zone. These systems can be made more efficient by turning them into variable airflow systems. So instead of being constant volume, now they would be variable volume. They're doing functionally the same thing in practice. They're still mixing hot air and cold air before we're delivering it to the space. But if we can vary that total supply air, if we can vary the CFM of the hot deck and the cold deck, we can make this quite a bit more efficient. We're still mixing it, but if we're in that condition where our thermostat says we're perfectly happy where we're at, we don't want heating and we don't want cooling, then we can turn down the airflow. And so rather than always sending the same amount of air to every single zone, by making it a variable flow system, we can cut back that airflow and save a whole lot of energy. In this scenario, in my diagram, I showed a single fan serving both coils. That would be more appropriate for an older style constant volume system. In a variable volume system, what's more common is for the hot deck to have its own fan and the cold deck to have its own fan. And then both of those fans can ramp up and ramp down depending on what's needed out in the space. So if you have a bunch of zones that are saying, hey, we're happy on the, or a bunch of zones saying, we don't need any cooling, then your cold deck fan can turn way down. And then now you're not just having the heating and cooling systems fighting each other. If you can do this, you can make this significantly more efficient than a constant volume system. The big kicker as to why is that reduces the amount of simultaneous heating and cooling by reducing the airflow in whichever airstream you don't want that air from. And if we are lowering the total airflow supplied by the fans, that means our fan energy as well is going to be less. We won't spend a whole lot of time talking about variable volume dual duct and multi-zones, but it is worth a quick digression to talk about them. There is a possible retrofit strategy here as well, if you can convert a constant volume system to a variable volume system, but we will talk more about fan speed control in a later lecture. The last system type is what's called a single duct VAV system. Again, this is one air handling unit that serves multiple zones, each with their own thermostat. Different from these other systems, this is an extremely common system type to see in commercial buildings. When I run into this, it's not a surprise whatsoever because a lot of these systems are still installed today in new systems. What might be interesting though is the closest comparable system type is a constant volume reheat, which I already told you, constant volume reheat systems are terrible. That's the worst. The reason it's comparable, we are always supplying cold air and then we are reheating it as needed. So from that statement, well, man, that sure sounds like a constant volume reheat system, which I said was terrible. So why would we want this? And why do they still allow single duct VAV systems? The big reason is now we're varying the cold air. It's in the name, variable air volume, or VAV, through opening and closing some control dampers. So let's look at the diagram here. We have our air handler. It's got all the same major components as all the other air handlers. And we're still supplying cold air from the air handling unit, always in that 55 to 65 degree range. And we have this VAV box, which has a damper in it right there that can open and close to vary the amount of air that this thing is going to allow into the zone. And we have this reheat coil at every single zone. So whereas in a constant volume reheat system, that reheat would turn on to prevent the subcooling of the space, because remember, constant volume reheat, gas is on full 100% all the time. So when this thermostat starts to say, hey, we're getting kind of cold in here, it has to turn on the reheat to fight that cold air coming in. What's going on here instead is the first thing it does is it cuts back on the airflow. So instead of turning on the heat, it cuts back on the air. Thinking back to that car analogy, instead of turning on or pushing the brake, you're going to let off the gas. That seems like a much more efficient way to operate things. So we'll vary our airflow by opening and closing that damper. which we call a VAV box. The VAV box encapsulates the damper and the reheat coil. And this is what that box looks like. So we have our air coming in on one side. We have our damper here that can open and close. We have an actuator, a little motor to open and close that thing, a controller that's got the brains to do that. We have our reheat coil, and then our air coming out. If our box is in cooling mode, so if our thermostat says we need cooling, we're going to open and close this damper to increase or decrease the amount of cold air coming in. And that's how we maintain that temperature we want in those summer months. In heating mode, in the winter months, well, remember, we're still providing cold air through this VAV. So we don't want to provide excess cold air in those winter months, because then we're going to have the same problem that we have with a constant volume reheat system. So in heating mode, the box now becomes a constant minimum air volume system. So this damper will go to some minimum position, maybe 40% of its maximum, to provide ventilation air. And then we're going to turn on that heating coil as needed, depending on what that thermostat needs. So even though the system is called a VAV system, this box is really only varying the airflow in cooling mode. Once we get into those winter months and we're primarily in heating mode, this box turns into a constant volume system. But looking at the entire system, this box might be in heating mode, but the box next door might be in cooling mode. And maybe the box next door is still varying its airflow. And maybe on your high-rise building, you have 100 of these boxes connected to the same system, and some of them are in heating and some of them are in cooling. The overall system is still VAV, even if individual boxes are operating in that constant volume mode. So as our boxes are opening and closing, depending on what's going out here at each zone, how do we think this fan is going to respond? And the short answer, this is all I'll give you today, we'll get into this more later. The speed of this fan at the air handling unit is going to increase or decrease. It's going to ramp up and down to meet whatever airflow sum is required at all of the VAV boxes. So maybe in full cooling mode, all of the boxes on your system, we need to output 10,000 CFM, and the fan will ramp up to a high speed to deliver 10,000 CFM. But then in the winter, when they're all cutting back and they're at their minimum positions, maybe we only need to output 5,000 CFM. There are a lot of, maybe not a lot, there are a few different ways to control fan speed, and we'll get into that down the road. And it's important to note, this type of system still requires that reheat energy, similar to a constant volume reheat system. It's just an inherent issue with this type of system. It's an inherent inefficiency with it. They generally call this the reheat penalty. But compared to a constant volume reheat system, a VAV system has a drastically reduced reheat penalty. If you design one of these systems well, these can be extremely efficient. But that's the trick, is designing it well. There is a way to design the system poorly, or maybe you design it perfect and then you hand the keys over to the owner, and if the owner doesn't have a great understanding of how this system is supposed to work, they can screw things up pretty bad. One more video, again, 12 or 13 minutes, but I think it's well worth the watch to help illustrate this with some animations. Last slide. If any of this isn't clear, not understood, Google and YouTube is your friend. So the videos I've linked in these slides, I have those links on Blackboard as well. And always recall those fundamentals. If we're talking about airside HVAC, it's all about delivering hot air or cold air to a space. All of these systems, even though they are drastically different in how they do this, that's ultimately what they're doing at the end, is delivering hot air or cold air, which is our useful output to serve the load. Quick example. If my goal is to deliver 2000 CFM of air at 55 degrees, no matter what system is doing that, that is the same output. That's the end result at the end of our process. That's the useful part of our system. We're delivering 2000 CFM of air at some temperature. But depending on what type of system you have, if you're doing that with single duct VAV versus constant volume reheat, the input to deliver that output can be drastically different. So there are efficient ways to deliver that air, and there are inefficient ways to deliver that air. There are some other system types we're not covering, but generally speaking, they are some kind of variation on the ones we've talked about. If you watch those YouTube videos, they do go a little more in depth. And for example, when we're talking about VAV systems, there's a variant on it called a fan-powered VAV system, which has a VAV box, but there's a little fan in the box that helps with air circulation. That's the short answer. I'm not going to get into the depth on that, but if you watch those videos, you will get a little bit of a taste of some of those other variants on these system types. We're also not going to spend a ton of time on newer emerging technologies. The types of systems we talked about today, that's mostly what we see in existing buildings. You're generally not going to do an energy audit and find a top of the line, brand new, super efficient system. What I'll probably do, which is what I did last year, is on the last day of class before the final, I put together a final set of slides that talk about some of the newer or maybe less typical HVAC systems you might see out there. So I'll briefly touch on it, but as far as the course in your homework, we won't be spending a ton of time on it. That's all I got. Any questions? I know there was a Gonzaga game. Don't spoil it for me. If you do, I'll fail you. All right. All right. Well, I'll stick around for 15 minutes, but otherwise, have a good weekend. And just a reminder that Tuesday is just kind of a free day. If there's anything in particular you want me to talk about, any kind of special topic, just shoot me an email.
Thank you.
Thank you.
Thank you.